In this video I'm going to be talking about the factor and remainder theorems, how to use them and what they are. So we'll start with the remainder theorem, and it helps if we actually do a division first and see what the remainder comes out as. So if you don't already know how to do polynomial division, I would advise looking back at my video on that. But we're going to go ahead and divide 3x squared plus 4x plus 4 and divide that by x plus 1. So our answer, if we do the division, is 3x plus 1, remainder 3. And this is important for our remainder theorem. If we think about what this actually means, it means that when we divide 3x squared plus 4x plus 4 by x plus 1, we end up with 3x plus 1 lots of x plus 1, and then 3 left over. So we could write this as 3x squared plus 4x plus 4 is actually equal to 3x plus 1 lots of x plus 1, add 3. The remainder of 3 down here tells us that 3x plus 1 lots of x plus 1 isn't quite enough, we need 3 more. If you're not quite sure where that comes from, think of a really simple division. So if we were to divide 17 by 5, how many 5s into 17? That goes 3. 3 5s is 15, so a remainder of 2. So 17 is actually equal to 5 lots of 3, and then we need to add our remainder on because 5 lots of 3 is 2 too few. So writing it like this helps us understand the remainder theorem, because what we do with the remainder theorem is this bit obviously is our remainder, the 3. So if we can find some way of making this bit equal to 0, then we will only be left with our 3. Now 3x plus 1, we didn't know that until we'd done the division, but the x plus 1 was our divisor. So if we make x plus 1 equal 0, then that will make this whole term disappear, because anything times 0 is 0, and leave us with just our 3. For x plus 1 to equal 0, x must be minus 1. So if x is minus 1, then 3x squared plus 4x plus 4 equals 3. Only when x is minus 1, but this is really useful because if we are dividing by x plus 1, if we make that equal 0 by choosing a value of x that makes it 0, plug that into our equation, we get our remainder. Let's just double check that works then. So if I choose x equals minus 1 and plug it into my equation, I get 3 times minus 1 squared plus 4 lots of minus 1 plus 4 equals 3, because minus 1 squared is plus 1, minus 4 plus 4, which is 3. So plugging in minus 1, x equals minus 1, into our equation, substituting x for minus 1, actually gives us our remainder if we were to divide by x plus 1 up here. So this is really useful for if we don't particularly care about the quotient, if we don't care about the 3x plus 1, but we need to know what our remainder is. It's also useful going the other way. If you have ever done synthetic division, you can use synthetic division to get your remainder, and that actually would give you the answer for a certain substitution, and sometimes that's easier than doing the substitution itself. It also leads on to the factor theorem, which is very useful for factorising, and we'll look at that in a minute. But let's just generalise this a little bit first. So if we take p of x, which is a polynomial function of x, so it is an expression with x terms in only and no negative or fractional powers of x. So we've got a polynomial that is a function of x, and we divide it by x minus c, which is a linear term where c is a constant. So it could be x minus 1, x minus 2, x plus 3, which would be minus 3. So c could be anything as long as it's a constant, and we've got a polynomial x. If we do that division, we're going to end up with a quotient, which will be a function of x, so that's our answer above our bus stop, so that would end up here, and we might end up with a remainder r. So this is our quotient, which is a function of x, and we might end up with a remainder, which I'm going to call r. So more generally, as discussed a minute ago, we could then say that our polynomial function of x must be equal to our quotient times our divisor plus our remainder. So if we now in this equation make x equal to c, so for x equal c, and remember c comes from our divisor, then p of c must equal x minus c becomes c minus c, which is 0. So our quotient times 0 is 0, and we're left with just our remainder. So you can see that this can be a lot easier than actually performing the polynomial division. So if you're not interested in what the quotient is, but just want to know what the remainder would be, you can plug in your value. So if we were dividing a polynomial by x minus 3, you would want to plug in the value 3. If we were dividing our polynomial by x plus 4, we would want to plug in the value minus 4, because plus 4 is minus 4. So this tells us our remainder, which in itself isn't that useful, but there is another more useful use, which is the factor theorem. But first let's discuss the limitations. This only works when the denominator or divisor is linear. There is actually a reason for this, which you can find out about by watching one of my other videos, but for now we are going to continue with the remainder theorem, but remembering that it only works when you are dividing by a linear expression, so when it is of the form x plus or minus a constant, so there are no x squared terms or higher. So let's have a look at how we can use the factor theorem to find the remainder without having to do polynomial division. So I'm dividing by x minus 2 here, and I know that if I make my divisor equal to 0, so if x equals 2, then the polynomial with 2 plugged in, so the top, the numerator, will equal my remainder. So p of 2 is going to equal 2 cubed plus 4 lots of 2 plus 3, which is 8 plus 8 plus 3, so 19. So my remainder would be 19. Now you can do the polynomial division to check it if you like, but you can see this is a lot quicker than actually going through and doing the polynomial division. So pause the video and test yourself and check that you can use this to find the remainder of this division. So this time we want to make x plus 1 equal to 0, so we need x to be minus 1. So if we call the top p of x, if we find p of minus 1, that will give us our remainder. So p of minus 1 is equal to 2 times minus 1 cubed plus 3 times minus 1 squared plus 1. Minus 1 cubed is minus 1, so that's minus 2. Minus 1 squared is plus 1, so that is 3, and then plus 1. So we've actually got 2 as our remainder here. So as I mentioned earlier, the factor theorem comes from the remainder theorem and is very useful for finding factors of polynomials. So if you wanted to factorise a polynomial, particularly ones that are x cubed or of higher degree, then it can be very difficult. The factor theorem gives us a shortcut way so that we don't have to try lots of different divisions to find the factors. So to understand the factor theorem, it helps if we really make sure we understand what a factor is. So a factor is something that goes in exactly. So for example, if I do 12 divided by 4, that is 3, and it goes in exactly, so the remainder is 0. If I pick another factor, 12 divided by 6, that would be 2, again, remainder 0. If I pick something that's not a factor, so 5, that goes in twice with a remainder of 2. 2 lots of 5 make 10, so we've got a remainder of 2. So this is what's important here. If it is a factor, the remainder is 0. So we can use that with the remainder theorem to find factors of polynomial expressions. So remember, our remainder theorem tells us that if we are dividing by x minus c, then p of c will equal our remainder. When x minus c is a factor, that means that there is no remainder, or the remainder is 0. So if it is a factor, then p of c will equal 0. So we can use this to find factors of polynomial expressions. So let's start simple to see how it works. So I've got a polynomial which is a function of x, and my function is x squared plus 3x plus 2, and we want to factorise this. Now, if you know how to factorise quadratics, you can probably just do this, but we're going to look at how to do it using the factor theorem to see how it works. So we just try some values. So if we try x equals 1, then p of 1 would be 1 squared plus 3 times 1 plus 2. That would be 1 plus 3 plus 2, so 6. Clearly not 0, so substituting in 1 doesn't give us a 0 remainder, which means that x minus 1 is not a factor. Remember, the value that we substitute in is the value that makes our divisor 0, so it's x minus 1, not x plus 1. So I can see if I try positive values it's not going to work because it will just get bigger and bigger. So I'm going to try x equals minus 1. So this time if I do my function with minus 1 substituted in, I get minus 1 squared plus 3 times minus 1 plus 2. Minus 1 squared is plus 1, minus 1 times 3 is minus 3 plus 2. So this time it does equal 0. So now I know that if I divided by x plus 1, then my remainder would be 0, so it is a factor. So we have found one of our factors for our original polynomial. We can now go ahead and do polynomial division with that factor to find out what is left. So if we quickly do the x squared plus 3x plus 2 and divide that by our known factor x plus 1, and we can see our remainder is 0. So we know that x squared plus 3x plus 2 is actually equal to x plus 2 lots of x plus 1, and it goes in exactly, there is no remainder. So it allows us to factorise polynomials. Obviously this one could have been done by sight if you know how to factorise quadratics. However, it can become very useful when trying to factorise higher polynomials, higher degree polynomials. So in this case we've got a cubic. That is more difficult to factorise by sight. We could try dividing through by some factors to check if we get any that don't have a remainder, but that is quite time consuming and tedious. So I'm just going to try some different values until I make it equal to 0, because then I know what my factor is going to be. Now I'm going to choose the simplest values of x to begin with and the smallest values. Because the numbers in my polynomial are quite small, I'd expect the numbers in my factors to be quite small. They won't necessarily be, but it's easier to substitute in smaller numbers, and it is more likely that you will be given a question with smaller numbers in it. So start with smaller numbers. So I'm going to start with 1, minus 1, 2, minus 2, but it could actually be anything. So if I try 1, I get 1 cubed minus 7 lots of 1 minus 6. 1 minus 7, that's going to be minus 12 in total. So clearly x minus 1 is not a factor. So let's try plugging in minus 1. So minus 1 cubed minus 7 lots of minus 1 minus 6. Minus 1 cubed is minus 1. Minus 7 times minus 1 is plus 7. Minus 6 equals 0. So here I have 0 remainder, which means that x plus 1, because I plugged in minus 1, is a factor. So I can now know that it is worth doing the division because x minus 1 is a factor, and when I do the division it will give me what's left to still factorise. Remember, when we do the polynomial division we need a column for every power of x, so I'm going to add a 0x squared in there, minus 7x minus 6. And we now know that we can divide this by x plus 1. As expected, no remainder. So now we know that we can actually factorise our polynomial into x plus 1 lots of x squared minus x minus 6. Obviously this isn't fully factorised yet because we can now factorise the x squared minus x minus 6. Now you might actually end up with, at this point, a quadratic here that doesn't factorise down any further, in which case you just stop. This would be fully factorised. But if you have been asked to fully factorise an expression, or you need to fully factorise an expression, you need to check the quadratic to see whether or not it does factorise before stopping. So if it doesn't factorise, leave it as it is, but this one does factorise, so we are going to continue and factorise the x squared minus x minus 6. So x squared minus x minus 6. We could do it in the same way, test some values of x to find out what our factor is, and then do the polynomial division, but I find it easier with quadratics, especially with only one x squared, to just factorise. So we need two numbers that add to give us minus 1 times to give us minus 6, so I know it's going to be minus 3 and plus 2. So the x squared minus x minus 6 up here factorises down to x minus 3x plus 2. So I can actually factorise this even further, and I've got x minus 3, x plus 2. So we have now fully factorised our cubic into 3 individual brackets. So test yourself, pause the video and try and factorise this polynomial that's actually got degree 4. So I don't want to try lots of different polynomial divisions, so I'm going to plug in some values for x. So if I call this p of x, I'm going to first try p of 1. So p of 1 would be 1 to the power of 4 plus 1 cubed minus 7 times 1 squared minus 1 plus 6, which is 1 plus 1 minus 7 minus 1 plus 6, which equals 0. So I've actually already found a factor, so that was using 1, so that tells me that x minus 1 is a factor. So now I can do the division and I can divide my polynomial by x minus 1. So I've done the division here for you, so if you want to pause and have a look at that you can, but this division tells me that there was no remainder, so it was a factor as expected, and I can now factorise x minus 1 out of this polynomial, and that would leave me with x cubed plus 2x squared minus 5x minus 6, which was our quotient here. So we're starting to get there, but now we need to factorise this bit we haven't fully factorised yet. Now there's no reason we couldn't have another factor of x minus 1, so I'm now going to call this q of x, and I'm going to try q of 1. So that would be 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6 gives me 1 plus 2 minus 5 minus 6, which is 3 minus 2 minus 8. So that is not working, so x minus 1 is not a factor. So now let's try q of minus 1. That would give us minus 1 cubed plus 2 times minus 1 squared minus 5 times minus 1 minus 6, which gives us minus 1 cubed is minus 1, plus 2, because minus 1 squared is plus 2, plus 5 minus 6. So that, if you add it all up, equals 0. So this one works, which because we had minus 1, tells us that x plus 1 is a factor. So I can now divide q of x by x plus 1 and see what's left. So I've done the division for you, and again you can pause it and have a look, but that tells me that it goes in with no remainder as expected, so it is a factor. And now the q of x can actually be factorised, and that was x plus 1 lots of x squared plus x minus 6. So now we're left with a quadratic to factorise, so let's call that r of x. So if r of x is x squared plus x minus 6, it is a quadratic with a single x squared, so I'm just going to factorise that, and it's actually the same one we had earlier but the opposite signs, so x plus 3 and x minus 2. So now I can fully factorise down my p of x into 4 linear factors, which are x minus 1, x plus 1, x plus 3 and x minus 2. So actually the thought of having to factorise something like that can be quite daunting, but using the factor theorem it is actually relatively easy. Obviously you have to do a bit of trial and error to begin with to find the factors, but once you have, it makes life a lot simpler, and we've managed to factorise this this degree 4 polynomial down into 4 individual linear brackets. So just a quick recap. The remainder theorem allows us to find the remainder of a polynomial without having to do polynomial division. So if we wanted to divide by x minus a and we were only interested in the remainder, we could plug plus a into our equation, substitute it in for x, and that would give us our remainder. To use our factor theorem, our factors are when we have no remainder. So if p of a equals 0, then x minus a is a factor. So it can be very useful for factorising polynomials, particularly of cubes or degree 3 or higher. So I hope that was helpful, and I will see you again soon.